Hello. Hello, everyone. Welcome to the second multi-party computation section. We're going to have our first speaker, Alexandra Binstock. So, please.
Okay, yeah, thanks for the introduction. So today I'll be talking about how to build topology hiding computation from oblivious transfer. And this is based on joint work with Marshall Ball, Lisa Cole, and Pierre Meyer. Okay, so first of all, what is topology hiding computation? And for this, I'll start by defining secure multi-party computation. Here, we have n parties down at the bottom, and they have some private inputs, and they want to work together to privately compute a function of their inputs. And what I mean by privately is that an adversary corrupting possibly many of the parties should learn nothing beyond the inputs of the corrupted parties and the output. Okay, and of particular note for this talk, typically in MPC, we assume secure point-to-point communication channels between all of the parties. While this might be a reasonable assumption to make for this case of 9 parties, as the number of nodes goes up, this graph gets very complex, so maybe it's infeasible to have all of these connections. Maybe instead, we have this incomplete network here. So this begs the question of, should we keep features of this topology private? And this is maybe motivated by the setting in which the topology is based on location data. For example, if you're communicating with vehicle to vehicle communications, or if the connections are based on users' relationships, for example, in a social network. Okay, but what exactly do we mean by topology privacy? So for this, let's bring back this graph, and let's assume that P6 is corrupted. So before the protocol even begins, what does this party see? It just sees its local connections in the graph, so its neighbors in the graph, and nothing else. So what we want from THC, in addition to the standard MPC guarantees, is P6 should learn nothing else beyond its local view. Okay, so a bit more formally, and this was first defined by MOR15, we say that a protocol pi is a topology hiding computation protocol for a graph class G and a functionality F. If, let's say, P6 is corrupted, then there exists a simulator, which on input the graph class, the corrupted party's input, the output, and the corrupted party's local view in this graph can output a distribution that's indistinguishable from the view of the party in the real world. Okay, and this definition naturally extends to many corruptions. So in other words, again, the protocol should reveal nothing beyond the input and output, as well as the neighbors in the graph of the corrupted parties. And as usual, we can consider a different number of corruptions, a passive or an active adversary, and a static or adaptive adversary. But for the sake of this talk, we'll focus on passive static adversaries. So before I move on to our paper, I just want to motivate a little bit, why is THC hard? And why is it hard even for passive adversaries? And for this, I'll talk about the flooding broadcast protocol, where we have a broadcaster in the middle here, and he wants to send a message to all of the parties in the protocol. Okay, so what it'll do is it'll first send the message to its neighbors, and then all of these parties will send the message to their neighbors. Okay, and of course, this is trivially secure in traditional semi-honest MPC or passive MPC. But for topology hiding, each party, so for example, this P3 up here, it learns its distance from the broadcaster and also the distance of its neighbors to the broadcaster. And so this is not topology hiding. For example, if this edge was missing, then P3 would see a different distance for P4 from the broadcaster. Okay, so now on to the question that we study. It's a well-known fact that oblivious transfer and MPC are equivalent. And you can easily see that THC trivially implies oblivious transfer. But what we ask in our work is, does oblivious transfer imply THC? So let's start with some known results in this regime. First of all, MOR 15 said that if you have a constant round MPC protocol with constant overhead, then you have THC for graphs with constant degree and logarithmic diameter, okay? Later, in a series of works in 2017 and 2018, they showed that if you have this key homomorphic re-randomizable encryption primitive, then you can get THC for all graphs. Okay, with the caveat here being that this encryption primitive is only known from structured algebraic assumptions like QR, DDH, and LWE. So what we do in this paper is we show that if you have constant round 2PC with constant overhead, then you can get THC for semi-honest static adversaries, corrupting all but one parties for all graphs. Okay, so we're not quite there at getting THC from just general OT, but we're a step closer here. So along the way, we define this locally simulatable MPC for any fixed graph notion. Then we show that using this notion, as well as the correlated random walks idea from ALM 17, you can reduce THC to just building a locally simulatable OR protocol on the path. Okay, and finally, we construct such an OR protocol from constant round 2PC with constant overhead. So in the remainder of the talk, I'll dive into these 3 points. First, let me recall this correlated random walks idea from ALM 17. Here, for each time step, every node in the U, every node U in the graph defines a permutation on its neighbors. So for example, at time step T1 here, U maps P4 to P2, P2 to P6, then P6 to P4. Then in the next step, it maps P2 and P4 to each other and P6 to itself. And what we get from these permutations is several correlated random walks. So for example, we get one walk that goes like this from you, another one like this, another one like this. And in fact, we actually have walks in this picture that should start from every node, not just you. And what I mean by correlated here is that there's exactly one walk through each edge at each time step. Okay, and I'll tell you later why this is important. What I mean by random is that if you look at each individual walk, they are actually a random walk. And this is important because basically later for correctness, we'll use the properties of random walks to show that if each walk is long enough, then every node in the graph will be reached. Okay, and so why is this useful? Well, maybe we can just design protocols for paths now, which should be an easier task. And for this, I'll start with defining locally simulatable MPC on a path. So let's say we have an MPC protocol, and these two nodes, 4 and 8, correspond to corrupted parties. Usually for MPC, we say that we have a simulator that can take together the inputs and the output of both parties, 4 and 8, and simulate their views in the protocol. We now have a new requirement where we mandate that we can simulate the views of these two parties independently. So namely, given independent randomness and the parties' individual inputs and output, we can simulate the views. So now let me show you how we can reduce THC to locally simulatable or on a path. First, I want to mention this fact that once you have topology hiding broadcast, you can pretty easily build THC. And that's because once you have THB, you can first instantiate topology hiding secure channels using key exchange. And then with these secure channels, just use any standard MPC to get THC. Okay, and then broadcast itself can be instantiated by just the OR function, where the broadcaster inputs the broadcast bit, and then everyone else inputs 0. Okay, so now let's build this THB protocol. And it's very simple. Once you have this locally simulatable OR in a path, you just build correlated random walks, and for each walk, run the locally simulatable OR protocol. And so correctness should be somewhat clear, because each walk will cover the whole graph. Every party in the protocol will get the correct output of the OR. For security, let's start by looking at 2 executions of the protocol. So on the left, we have a random walk that starts at P6, then goes to P4, and then goes to P3 as the 3rd node. On the right, we have one walk that starts at P6 as the 1st node, but then goes elsewhere. And then another walk that starts elsewhere and ends at P3 as the 3rd node. Or not ends, but it goes to P3 as the 3rd node. And I argue that by using locally simulatable, even though the simulator doesn't know which of these walks actually happen, it just needs to locally simulate the view of P6 as the 1st node on a path protocol and P3 as the 3rd node on a path protocol in both of these worlds. Okay, and actually, all it needs to do is for each time step t, it just needs to simulate independently P3's view as the tth node on some paths. Okay, and the same for P6. So in particular, for time t equals 1, it just needs to simulate P3's view as the 1st node on this path and the 1st node on this path. Okay, then at time t equals 2, it just needs to simulate P3's view as the 2nd node on some path coming from here and some path coming from here. Okay, and this just can be done using local simulation. And in fact, you can look at the view of each individual corrupted party independently. And this again, this is where we ended up using the correlated part of the random walks, because basically you just need to simulate on each incoming edges the OR protocol. Okay, so now with the time remaining, let me explain to you the locally simulatable OR. So if you have 2 parties, then it's easy. We can just run a 2PC directly between these 2 parties. If we have 4, I claim that we can still do this, okay? And what we'll do is for the 2 parties on the left, we'll use a 2PC to emulate this P00 protocol, party in this protocol on input X10 or X11. Okay, and we'll do the same thing for the 2 nodes on the right. And in fact, we can keep doing this recursively. So for n equals 8, we'll just use the first 2 real parties to emulate the party in this 2PC. Okay, and so on. And you can see why do we get locally simulatable? Well, for this node, we just need to simulate the 2PC interaction here, which we can easily do. And for this node, we just need to simulate the the 2PC interaction here. And also for this node, we need to simulate the 2PC interaction here. And there's some subtleties here, but more or less, you can make this go through, and each of these simulations that I just mentioned are in fact independent. Okay, so just some quick remarks. The MOR15 is also similarly based on an recursive MPC protocol. But here, for paths, the diameter is n, so it's too inefficient. And so in fact, our protocol is efficient enough to handle this case. I'm running out of time, so maybe I'll skip this. But just to conclude, so we build THC from constant round 2PC with constant overhead. And this is the first such result for all graph classes. And we define along the way this locally simulatable MPC notion, which might be of independent interest. Of course, still open is the question of building THC for all graph classes from general polynomial around oblivious transfer. Okay, thanks for listening.
We'll have time for a quick question.
If you want THC for NC0 functions, do you get it from OT, like say in local PRGs? Because from local PRGs, or if you have a constant over 2PC without constant rounds, this is totally useless for you.
Yeah, I mean, so like if you go to this picture, basically both, so if you have like round complexity R for your 2PC protocol, then the total complexity will be like R to the log n.
Mhm.
So it needs to be constant.
Okay. But say for NC0 functions you do have, and then can't you use garbled circuits to reduce everything to NC0?
Yeah, I think in that case you could probably do it. Yeah.
So then maybe OT plus local PRGs should give you what you.
Yeah.
Okay, so let's thank the speaker again and take the questions offline.
Hello, I'm Ananya, and I'll be presenting our work on network agnostic statistically secure MPC. This is joint work with Ashish Chowdhury. So what is MPC? With MPC, we have mutually distrusting parties who want to compute a combined function of their private inputs without revealing their private inputs. So to do this, ideally, all the parties would send their inputs to a trusted third party who will compute the function and return the output to all the parties. So this is what we want in the ideal world. And to achieve this in the real world, we use MPC, where the parties run a distributed protocol over a network to finally learn the output without revealing any of their inputs. To model the distrust in the system, we use a centralized adversary who can corrupt a subset of the parties. And we assume that the adversary is malicious, which means that it can arbitrarily deviate from the protocol code. Now, we assume that each pair of parties is connected by a private and authenticated channel. And there are usually two kinds of networks which are studied in the literature. With synchronous networks, any message sent can be delayed only by a finite time, which is delta. But this is difficult to realize in practice, and real-world networks are better modeled by asynchronous networks, where any message sent is just delivered eventually. But it's difficult to design protocols in asynchronous networks since a receiver cannot wait indefinitely for a message from a sender, as the sender may be corrupt and may never send the message at all. So because of this, parties have to proceed to the next step of the protocol by foregoing some messages, and these messages may be from some honest parties as well. Okay, so that was the two types of networks. And now we'll look at the types of adversaries, which are usually studied in the literature. So the more common notion of an adversary is a threshold adversary, where we say that up to a certain threshold, number of parties can be corrupt. And this threshold is usually a fraction of the total number of parties. So here on the left are these colored sets represent possible corruptions in the threshold setting. And a less studied notion of adversary is a non-threshold adversary, where instead of just giving a number, we explicitly write down the sets of possible corruptions. And because of this, you can have a possible set of corruptions like the one on the right, where one set of parties, the blue set here, is much larger than the other sets of possibly corrupt parties. And here, instead of saying that up to a third of the parties can be corrupt, we say something like no three of the possibly corrupt parties can cover the entire set when you take their union. So intuitively, the non-threshold setting is telling that the power with which an adversary can corrupt a party may not be uniform and may differ from party to party. So to understand this with more examples, MPC is possible in an asynchronous network as long as up to a third of the parties are corrupt. So if we have 5 parties, then one of them can be corrupt at once. And in a non-threshold setting, MPC is possible as long as the adversary structure, so this set Z here, is the adversary structure which explicitly mentions the sets of possible corruptions. And MPC is possible as long as this satisfies the Q2 condition, which means that if I take any 2 sets from this adversary structure and take their union, and that does not cover the entire set of parties. And with the example here, we are saying that P1 and P2 can be corrupted together, or P3, P4, and P5 can be corrupted individually. So notice that with a non-threshold setting, I can tolerate 2 parties being corrupt, and on the threshold, I could only tolerate 1. So immediately it is slightly better than the threshold setting. But the downside of the non-threshold setting is that the adversary structure can be exponential. The size of the adversary structure can be exponential in the number of parties, and this might cause a communication blow-up. So MPC is possible in a synchronous network as long as up to half of the parties are corrupt. So if I have 5 parties, now I can tolerate 2 corruptions at a time. And with the non-threshold adversary, it's possible as long as the adversary structure satisfies the Q2 condition, which means that if I take any 2 sets from the adversary structure and take their union, then that won't cover the entire party set. So with this example, we are saying that P1, P2, and P3 can be corrupted together, or P4 and P5 can be corrupted individually. So notice here that with the synchronous network, we can tolerate more number of corruptions than we could in the asynchronous network, since we can tolerate up to half of the parties being corrupt. And so we look at the question of whether we can design an MPC protocol which works in both synchronous and asynchronous networks while giving the best possible guarantees in both networks. That is, we want to be able to tolerate more number of corruptions in a synchronous network than an asynchronous network. And the rationale behind this line of work is that networks may not be purely synchronous or purely asynchronous. At times they can be synchronous, at times asynchronous. And irrespective of the network type, we want to be able to give the best possible security guarantees. And prior work has looked at this for computational and perfect security, and we're the first to look at this with statistical security. And we show that it's possible as long as the Q2 condition is satisfied. So now we have 2 different adversary structures. The synchronous one, which lists out the possible corruptions in a synchronous network, and the asynchronous one, which lists out the possible corruptions in an asynchronous network. And the Q2 condition means that if I take any 2 sets from the synchronous structure and any 1 from the asynchronous structure and take their union, then that won't cover the entire set of parties. So that's the problem statement. And let's look at the solution now. I'll give a high-level overview of one part of our solution. So the parties want to compute a function in MPC, and they represent this function as an arithmetic circuit of addition and multiplication gates. And the protocol would be something like this. So each of the parties will secret share their inputs. And once you have secret shares of 2 input wires, you can compute the secret shares on the output wires. And this keeps going in a layer by layer fashion until you have secret shares of the output and you reconstruct these. So in order to come up with our MPC, we had to come up with a lot of building blocks and subprotocols for the network agnostic setting, but I'll specifically focus on our verifiable secret sharing protocol for this talk. And for VSS, we require 2 building blocks. The first is broadcast, which allows a sender to send a message uniformly over the network. And the second is an IC signature, which is a statistical or unconditional equivalent of a digital signature, which allows a signer to sign a value to an intermediary who can then reveal this value to a receiver. And the guarantees of the signature scheme are that the intermediary cannot reveal a value which was not signed by the signer, and that the receiver will not learn this value until the intermediary reveals this value. So coming to our VSS, we use replicated or additive secret sharing, where the dealer splits its secret into L parts, where here L is the size of the synchronous adversary structure. And the dealer then takes the complement of every set in the synchronous adversary structure and gives the share to all parties in each of these sharing sets. The reason why this works is that one of these sets is the actual set of corrupt parties. So the complement set has only honest parties. And the share corresponding to this complement set will not be learned by the adversary and acts like a one-time pad or mask and hides the secret. So for now, let's refer to these complement sets as sharing sets. And the two main goals of DSS are first to ensure that the shares are uniformly distributed to all parties in each sharing set. And second, that the adversary will never learn the share corresponding to the honest sharing set. So I'll go over a synchronous VSS and we look at why it doesn't work in an asynchronous network. I'll then go over an asynchronous VSS and then we'll look at why it doesn't work in a synchronous network. And then we'll finally look at our network agnostic VSS. So with a synchronous VSS, I'll explain with an example so that it's a bit easier to understand. Suppose that we have 5 sharing sets and that the third sharing set is the honest sharing set. The dealer will split the secret into 5 parts and will send each share to all parties in each sharing set. The parties will then exchange these among themselves to check if they've received the same value, and they'll broadcast the results of these exchanges. The parties then construct consistency graphs where a node in the consistency graph is a party and an edge between 2 nodes indicates that the 2 parties receive the same value. So what the dealer does is it waits for a timer, which is the time taken by these broadcasts to complete. And then it looks at which of these sharing sets have consistency graphs which form a full clique. And by full clique, that means that the entire set of parties forms a consistency graph, which is a clique. So here, the first, third, and fifth sets are full cliques. And so the dealer will broadcast the shares for every sharing set, which is not a full clique. And why does this help us? Parties agree with each other because either the set was a full clique and they already agree with each other, or they agree with each other through the broadcast. And the share corresponding to the honest sharing set will never be revealed since that sharing set will form a full clique for an honest deal. But this does not work in an asynchronous network since we cannot rely on any timing assumptions and the dealer does not know when it's safe to broadcast these shares. So in an asynchronous network, the VSS would be like this, where the dealer will send the share, just like the synchronous case, to all parties in each sharing set. The parties will exchange these and broadcast the results of these exchanges, and parties construct consistency graphs. But now, instead of waiting for any timeout or any full clique to form, we'll wait for a partial clique to form in every single sharing set, such that these partial cliques are large enough to always contain an honest party. And this means that honest parties within each partial clique agree with each other. So what remains is for honest parties outside the partial clique to agree with honest parties inside. And to do this, we make the parties inside the clique reveal a collection of signed values from all other parties within the clique. And why does this work? This works because no corrupt party in the partial clique can reveal a value which was not held by the honest party in the partial clique due to the signature scheme. So this is great, but this does not work in a synchronous network since you may have more number of corruptions in a synchronous network, and these partial cliques may not be large enough to contain an honest party. So finally, coming to our VSS, just like the synchronous and asynchronous cases, the dealer will send the share to all parties in each sharing set. They will exchange these among each other and they will broadcast the results. And it's kind of a mix and match of the steps from the synchronous and asynchronous cases. So the dealer will wait for a timeout, which is the time taken by these broadcasts to complete in a synchronous network, but it will not do anything yet. It will keep waiting until the consistency graph of one of these sharing sets forms a full clique. And what we show is that if any one consistency graph forms a full clique, then the consistency graph corresponding to the honest sharing set forms a partial clique, which is large enough to have an honest party even in a synchronous network. So what the dealer does is it broadcasts shares corresponding to all to all sharing sets, which are not large enough even in a synchronous network to have an honest party. And so here the broadcast shares corresponding to 2 and 4. And with 3 and 5, we know that these partial cliques are large enough to have an honest party. So we'll use a method similar to the asynchronous case to ensure that everyone agrees on the same share. So that's all for thank you.
So thanks so much. Any questions? Can I go back to your conclusion slides? Or is there like any other like open problem we can work on?
Yeah. This is for the non-threshold case. So the threshold at the case is still open.
I see.
Yeah. That's the big one.
Okay, so thanks. Any more questions? Okay, if not, let's thank the speaker again. Okay, so next time we're going to have Substain copy talking about tumbling adaptivity in use protocols. Yeah, please.
For the introduction. So this is joint work with Ran Canetti, Dibia Rabi, Eduardo Soria Vasquez, and Sofia Jacopo. So first, I'll be talking a little bit about the setting, and now we're in the second FPC session, so I don't need to introduce what that is. But the main difference here is that what we're thinking about now is trying to scale up these protocols to work in a massively distributed setting. So rather than performing some computation collectively across these 4 parties, we instead want to think of what if we have thousands of parties that we perhaps want to outsource some sort of computation or responsibility to, and actually still perform some sort of meaningful computation. And this can be other things than FPC. We can think of like specialized things like threshold signing and so on. So we have these thousands of parties and we still want to perform some computation. And what does our adversary look like? So now we want to think of a quite powerful adversary. So I think the main difference here from what we've seen so far is now we'll have a lot of focus on adaptive corruptions. And that means that rather than the adversary beforehand selecting some fixed set of parties who will be our corrupted parties, we'll instead have an adversary who on the fly can decide who to corrupt. And if we think of these like massively distributed settings, kind of blockchain-like stuff, then you might imagine some sort of large-scale denial of service attack. That's still something we want to be robust against. And here, concretely, we want to think of some large corruption threshold. So here, T is some large constant fraction of our total number of parties. So think of C as a constant and N is our total number of parties here. And of course, something we really need to focus on when we have these thousands of parties is efficiency, because our traditional MPC techniques often don't scale particularly well as we increase the number of parties. So we need to have an especial focus on improving the efficiency and doing something smarter than just applying generic MPC techniques to this kind of massively distributed setting. So the core idea in the literature on this area is trying to outsource the computation to some particular small subset of the parties. So we select out some small number of the parties who get given some special responsibility, and our hope and we have some sort of mechanism, some sort of role assignment mechanism for this, and we expect these parties to kind of contribute and perform their role in the computation. And then, of course, for this to give us what we need, we want to preserve some sort of relationship between our threshold in the entire population with the threshold we get in this smaller population. And this kind of approach was codified in this You Only Speak Once paper by Gentry et al., where they described this approach where we have these parties who only speak once. And the reason we have that is because once a party speaks, it makes itself known to the adversary. So if the adversary knows that some party has some particular responsibility, then it could be adaptively targeted and corrupted. And that's what we want to avoid here. And of course, another thing we need is I need to be able to receive private inputs as a party that has some special responsibility. So I also need to be able to receive messages anonymously. And this kind of implicitly is via some sort of broadcast mechanism. So I can receive messages without the people sending to me knowing who I am, and I can pass on messages in a single action. And then if we combine this with secure erasure, so if I can erase my secret state before I speak, then that means that I can kind of pass on the torch and the responsibility before I'm able to be specifically targeted. So this is kind of the realm of protocols that we'll be looking at. So quickly, what do these synchronous Yoso protocols look like? So we have now, I'm going to introduce a term called committee. So essentially, we progressively have some subset who has a responsibility within our computation, and then they perform some local computation, send out a single message to the next committee, and we proceed like this. And then again, we need some sort of role assignment functionality to assign people to these special responsibilities. And this very quickly looks like a mess. So the way we tackle this in the literature in this paper that introduced the Yoso model, they kind of structured the approach to designing these protocols so we kind of avoid this problem of having to deal with the role assignment and everything else simultaneously. So what we do is kind of divide our world into two parts. So the first part will be something I'll be referring to as the abstract world. So here we're only thinking in terms of the committees, and here it's like abstract responsibilities within some whatever protocol we're trying to realize, and we give these some idealized communication functionality. So this could be something like a broadcast and a secure point-to-point model. And here, this allows us to more or less design MPC protocols roughly as we're used to, but with the caveat that we only have a single round of communication per party, more or less. And then we have something called the natural world, which is where we'll actually be instantiating our protocols, where we kind of map over to real world machines. And then we need to delegate these roles to the real world machines and actually need to realize the nomination mechanism and the communication infrastructure. And then, of course, to kind of bring this all together, we need a compiler to bring us from the abstract protocol over to our protocol in the natural world. And what does this compilation look like? So we have our abstract world protocol over here on the left, and then we want to kind of map these roles and assign them into the boxes. So here you can think of each box as a computer. And we essentially need to map our roles to real world machines. And then, of course, we want some sort of implication that abstract security implies natural security in some meaningful way. And this is kind of what we're going to pour into with our result, trying to see like what security guarantees can you get when doing this, this transformation here. So we need to kind of use the fact that we can kind of simulate in the abstract world to help us simulate in the natural world. And of course, our paper, we're not the first people to like build this compiler because, of course, when introducing the Yoso model, Gentry et al. Needed to introduce a compiler as kind of like a feasibility result and to show that this was something that kind of you were able to bring the parts of this model together. So what they were able to do, they were able to take information theoretic Yoso protocols, which Yoso implements some functionality. And here, Yoso implementing, you can think of this as like more or less UC, but with a few wrappers and caveats. And here it's against random adaptive corruptions. And that allows you to get a compiled protocol in the role assignment hybrid model, which UC implements secure functionalities against chosen adaptive corruptions. And the key thing to spot here is that there's a difference in the nature of the corruptions we're dealing with, because these random adaptive corruptions are modeled as the adversary essentially not having control over which particular roles it gets to corrupt when it goes to perform a corruption. And that's a significant reduction in the corruption power of our adversary, which makes it much easier to realize a secure protocol. So that's something that is a desirable property. Ideally, we want to make it as easy as possible to design a nice protocol in the abstract world and still get as strong a security guarantee as possible in in the natural world. And this is kind of what we'll be focusing on for our compiler. And there are a few caveats here. So for example, their role assignment functionality isn't realized, and they make very heavy use of non-committing encryption. And if you're familiar with non-committing encryption, you'll know that this is generally quite a heavy primitive and somewhat restrictive with respect to kind of the use cases we can get out of it. So what are some of the key ideas of this compilation approach? So one core idea is the idea of delayed honest role assignment. So here we can imagine that, okay, I don't know how well it's showing, but the boxes here on your right are red. And essentially we can imagine we have some set of currently corrupt machines. So what we want to make sure when we're kind of assigning out our roles and responsibilities is that we're not assigning any of our statically honest roles. So those are these blue circles. We don't want to assign these to any of the corrupt machines because we're not able to simulate the states of these honest machines, so we're not able to reveal them. So that's something we want to avoid. So for every role, we can kind of proportionally assign our statically corrupt roles to the currently corrupt machines. And that way we can kind of end up revealing the right proportion of roles to our adversary, but without being forced to reveal the currently honest roles. But here for now, I'm kind of avoiding the issue of adaptivity, and that's kind of the crux of a lot of these approaches and kind of what becomes difficult. Because we can imagine over in the abstract world on your left here, we have this static adversary and we can simulate that protocol. And that means that essentially, once we think of the natural adaptive world, once we've mapped over to concrete machines, then we're easily able to simulate communication that's going from honest parties to corrupt parties and from corrupt to honest. But we don't really know what messages are being sent between honest parties. And if you think of what this would look like in your typical kind of simulation, then like you would probably like replace your ciphertext with encryptions of 0 or something like that to kind of have like dummy values because you don't know what these concrete values that are being sent are. But of course, we want to kind of upgrade our security. So for the case of Gentry et al., they had random adaptive corruptions, but what we actually want to do here is something even stronger. What I'd actually like to say is, what if I can go from static security to get adaptive security? And the reason I want to do that is to kind of leverage the fact that intuitively, if the adversary doesn't know which machines have which roles, then it shouldn't have any advantage with respect to kind of targeting specific roles, which means that it can't target anyone specific. So I should be able to kind of make this static corruption, this adaptive corruption power actually map to static corruptions. But what happens if we kind of corrupt this machine, which is supposed to receive a message from an honest party? Then our simulation fails and we have a problem. Right? So what we can try and do to avoid this is then to, we kind of need to avoid having to open this message that is going to an honest party. So the way Gentry et al. Dealt with this was to say, okay, I have this machine being corrupted, but what if I can change the nomination? So they had this implicit assumption of, okay, I'm committing to having some nomination, but what if I can swap that party out? So this is where this random adaptive corruption comes in. So I go and make a random adaptive corruption, which means that some role which was previously honest is now corrupt. And then I kind of swap in this identity, and then I can replace this incoming message by taking my previous encryption, which had to be some like dummy value, and then replacing that with an encryption of a message in the underlying protocol, which meant that I can now take this kind of blue role, which I can't reveal, and replace it with this red role and substitute in the appropriate message that I've now learned from my adaptive corruption. But this, of course, requires non-committing encryption because I need to retroactively change the message that a certain ciphertext corresponds to. So I need to kind of equivocate for a message I didn't know, the simulator doesn't know at the time of encryption. And this, of course, is a very heavy primitive, and we'd like to kind of avoid that. So what we asked was, is there another way? So can we do this better and leverage this kind of visibility of our simulator in some sort of stronger way? So what we kind of observed is that we don't necessarily have to commit to some specific nomination. So our thought was, what if we, instead of kind of having a fixed mapping from these messages to whatever the recipient machine was, then what if I could select on the fly who the recipient was? So as my kind of protocol is running, if I could kind of choose where a message should go. So as a machine is activated, I can kind of target an honest role to that machine before it has a chance to be corrupted. And correspondingly, when machines are adaptively corrupted, I can correspondingly kind of map messages that I know from my simulator to this machine. And we can kind of proceed like this. And this way I can kind of adjust my mapping from roles to machines on the fly. And that means that I don't have to equivocate for my messages that I'm sending, but I just need to equivocate for my role assignment, which means that I can adjust my nominating committee, change how my nominating committees work. So here we have, or our role assignment works. So we combine the nominating committees approach of Benamuda et al. With key and message non-committing encryption from AsiaCrypt last year. And then this allows underlying protocol messages to just be in CCA encryptions. So we get a compiler which allows pretty much any YOSU protocol that implements some functionality against chosen static corruptions to be compiled to a protocol in a hybrid model where we have bulletin boards and a role assignment functionality, which UC implements the same functionality for a somewhat equivalent threshold. We also, as a to kind of complete this picture, we also realized the role assignment. Yeah, so we present a new compiler for synchronous YOSU protocols and get adaptive security from statically secure protocols. And we only need non-committing encryption for our nomination messages. Oh, sorry for the typo there. Yeah, we only need NCE for the nomination messages and none of the underlying messages. Thank you.
Any questions? If no, let's take the question offline, and thanks, speaker, again. Okay, so next talk is given by Yu Xia about broadcast optimal secure multi-party computation in the plane model. Please.
Thanks for introduction. Hi, everyone. I'm Yu Xia. Today, I'm going to talk about our work with broadcast optimal secure multi-computation in the plane model. This is a joint work with Michele Ciampi, Ivan Dangar, Divya Lavi, Luisa Senik, Lucky, and Sofia Jacopo. So previously, there are lots of amazing talk about MPC. So I hope everyone understand what is MPC. I do not repeat the definition here. So in this work, we focus on the following setting. First of all, we focus on plane model. Plane model means there's no trusted setup like a common reference string or public key infrastructure. Then we focus on malicious adversary, and we focus on the dishonest majority. The existing work shows that the optimal run complexity in this specific setting is 4 run. Namely, if you have 4 run, you can compute any efficient compute function. However, for this specific setting, we require all 4 runs over broadcast channel. And it is known that broadcast is really expensive. So in order to achieve 1 run of broadcast, you can either rely on the physical or external infrastructure like blockchain, or you can run the broadcast protocol by using lots of peer-to-peer runs to achieve 1 run of broadcast. So one natural question comes to our mind is that, do we really need all 4 runs over broadcast? Can we just replace 1 run or multiple runs with P2P runs? And what could be the best security guarantee we can achieve in this specific case? So in order to understand what will happen and to answer this question, we need to firstly understand what could be achievable security guarantee. Because we focus on the dishonest majority, so we know fairness is not achievable. Fairness means that if the adversary obtained the output, the honest party must also obtain the output. So usually we consider another group of security notion, which is security with different type of boards. I will introduce them one by one. First of all, it's a selective board. Selective board means that for every honest party, they could either abort or obtain the output of the function y. A stronger security guarantee is an anonymous abort. Anonymous abort means that either all honest party abort or all of them obtain the output of function y. Another stronger security guarantee is selective identifier abort, which means that for every honest party, they can either abort, identify one corrupted party or obtain the output from the function. Note that the different honest party can identify different corrupt party. It is allowed in this specific security definition. Finally, we consider the strongest security guarantee, which is identifier abort. It means that either all honest party decide to obtain the output of function y, or all of them abort and identify the same corrupted party. So it is important to note that we cannot compare whether the anonymous abort is more secure than selective identifier abort or not. There are some similar research compared to us, but all of them just try to investigate the two-run cases. For two-run protocol, it really requires the trusted setup, and it is still remain unknown for plain model case, and we are the first work to investigate what will happen. Then as for our results, first of all, we prove if you do not have a broadcast access, you can still achieve selective abort. Then if you want to achieve an anonymous abort, it is required that the last run must over broadcast. As for selective identifier abort, we require that we prove that it is required the first rerun over broadcast, you can achieve selective identifier abort. So finally, it is already known 4 rounds of broadcast is sufficient to achieve identifier abort, and our results show that it is also necessary for you to have 4 rounds of broadcast to achieve identifier abort. It shows that the upper bound matching the lower bound, and our result is really tight. Then in the remaining time, I want to talk about more details about the proof, how we prove possibility and impossibility. More specifically, I want to prove that why we cannot achieve selective identifier abort if we do not have a first rerun of over broadcast. I will use one specific pattern, which is first 2 run over broadcast and later 2 run over P2P channels. So we start with the 3-party protocol, and we can extend it to n-party protocol in the end. So we assume this protocol is selective identifier abort secure. And for simplicity, we consider functionality that only party out obtain the output. Then this proof consists of 3 steps. Let's go to the first step. Firstly, we want to prove that there exists an attacking scenario such that the party out must obtain the output. For the first step, the attacking scenario 1 is that the party 1 is corrupted and party 2 and party out is honest. On the first 2 rounds, on the first 2 broadcast rounds, everyone behave honestly. On the third round, party 1 will behave honestly to party out, but he will drop the message to party 2. And then in the fourth round, party 1 still behave honest to party out, but drop the message to party 2. Then in the end, the party 1 and party 2 will blame each other, say, well, I do not receive any P2P message from the other party. This is attacking scenario 1. Then in attacking scenario 2, this time party 2 is corrupted, and everyone behave honestly on broadcast round. On third round, party 2 behave honestly to party out and drop the message to party 1. On fourth round, party 2 behave honestly to party out and drop the message to party 1. And in the end, party 1 and party 2 will blame each other. At this moment, party out will get confused. Why? Because in the eye of party out, scenario 1 and scenario 2 are exactly the same. It means that if party out want to abort, he will identify party 2 in scenario 2. And then he will also identify party 2 as corrupted party in scenario 1. However, in scenario 1, party 2 is honest party. So based on the SIA security definition, he cannot identify corrupt party. It means that party out must able to obtain the output. And this concludes the first step of this proof. Then it's a second step of proof. What do we want to do? We want to use a attacking scenario to create a new secure protocol that is selectable secure. And it works as follows. So now we consider the new protocol and follow the same idea from the attacking scenario one. Note that the malicious behavior of party one in attacking scenario one now is only party's behavior in this new protocol for party P1 new. And we do some minor modification. First of all, because only party L obtained the output, it is not necessary to have the communication on the first round between party one new and party two new. So we do not want this message. And also only party L obtained output. So party L do not need to send the first round message to party one and party two. And intuitively, this protocol should be correct and private. So the correctness comes from that because in eye of party out, party one and party two are honest. And because this is honest behavior, it means that party out must be able to obtain the output from, This is come from the proof of step one. And the privacy hold is because now in the new protocol, we only have less message exchange. And we only want to achieve a weaker security guarantee, so it should work. And this concludes the second step of this proof. Then let's go to the final step of this proof. What do we want to do? We want to create a new adversary that can break the SA security we just proved. And this will reach to a contradiction. The core idea of step 3 is that now we want to create a new adversary that will internally run a simulator and try to extract input from only party one. If he succeeds, he can break the privacy requirement and reach contradiction. However, here we need to carefully handle the rewind mechanism. Note that in the play model, the only advantage the simulator has is he can rewind parties, but adversary cannot. So what we want to prove here is, even if the simulator do not rewind, he still have enough information to extract input from party one. And we need to prove it for all possible rewinding patterns. Then I will use one specific pattern as an example. So let's consider that the simulator wants to rewind the second round. Here is the simulator we want to use. This simulator is this simulator against corrupted party one and corrupted party out. And the simulator will have some interaction with the adversary. At some point, he said, well, I want to rewind the second round. I send a new second round message to party one. So here we design this adversary as non-rushing in the second round, which means that party one can only send a new third round message back to the simulator, which contains additional information from his input, which is helpful for simulator to extract the input for party one. However, according to the specification of this protocol, this message does not exist. Party one will never send the third round message to the simulator. So it means that even if the simulator do not rewind, he still have enough information to do extraction. Then what will happen in actual attacking scenario? So in actual attacking scenario, the adversary control party 2 and party L. The party 2 internally runs this specific simulator on the left-hand side, and they will communicate with each other. At some point, the simulator say, well, I want to rewind the second round. At this moment, party 2 do not need to send this message to party 1 because, as I explained before, this new rewind message will not provide additional information to simulator. So even if party 2 do not send this message to party 1, simulator can still extract, have enough information to extract if the simulator only want to rewind the second round. We do similar trick for also third round and fourth round. The remaining pattern is only for the rewinding of the first round. And the intuition behind that is that if the simulator rewind the first round, it is similar to start a new execution of this protocol. So by the security definition of MPC, it should be secure. And we refer to the paper for formal argument. And then up to this point, now we prove the simulator do not need to rewind the party to extract the input from party 1. So the adversary can safely internally run this simulator and then do extraction from the honest party one, which will break this privacy requirement of the underlying protocol, and we reach a contradiction. And this concludes my talk. So do you have any suggestions, questions? Yeah.
Any questions? If no, let's thanks the speaker again. Thank you.
Okay, can you hear me? Okay.
Okay, so next talk is by Amit Agwa about synchronized fair exchange. Please.
Hi everyone. So I'm Amit Agarwal and I will be presenting the work Synchronizable Fair Exchange on behalf of Ranjit Kumar Sen, Srinivasan Raguraman, and Adam Selfon, who couldn't make it in person due to several constraints. As a brief outline of today's talk, I will first provide a brief intro to Secure MPC, as well as security model and definitions we'll be working with. I will then introduce and define the primitive synchronizable exchange, or SYX for short. I will then go over the main result of today's talk, which is that two-party primitive SYX is complete for MPC with fairness. Briefly discuss how SYX can be pre-processed. Finally, we'll look at main takeaways and related results. So let's begin. So as you have already seen, MPC involves a set of N parties, each with their private inputs, connected by means of some communication network, which we usually assume to be complete, and possessing some computational abilities, which could be local computation or access to some hybrid functionalities. These N parties wish to jointly compute some function f on their private inputs to receive outputs y1 up till yn, respectively. They do so by invoking a protocol pi, which potentially makes use of the communication network and the computational abilities. We will assume for today's talk that the protocol works in discrete synchronous rounds. So when considering secure MPC, we'll be assuming that T out of N parties are corrupt and are being controlled by an adversary A. The T parties controlled by A can deviate in some manner from the protocol pi. And the way in which they deviate depends on the kind of adversary that we are dealing with. For today's talk, you may assume that the adversary A is malicious, static, rushing, and computationally unbounded. To capture the security offered by pi, we require that the adversary, despite controlling T parties and having access to their views, cannot learn anything more about the inputs of honest parties, apart from what is revealed from their own outputs. So MPC security is formalized using the standard real ideal simulation paradigm. In the real world, parties interact with each other and can use hybrid functionalities. In the ideal world, parties only have access to the ideal functionality, which takes in the input of all the parties, computes the output, and sends this output. And security requires the presence of an ideal world simulator, which can simulate the view of the adversary so that the real and ideal view is indistinguishable, which can be either perfect, statistical, or computational. However, the kind of security also depends on how the ideal functionality returns the output. For example, it can be guaranteed output delivery, fairness, or security with abort, as I will describe next. So the strongest flavor of security is guaranteed output delivery. Here, all parties submit their inputs to the ideal functionality, and the functionality just returns the output to all the parties. This notion of security is often hard to achieve, as an adversary can prevent the honest parties from receiving their outputs in many ways. Weaker notion is that of fairness, where all parties submit their inputs, An adversary can instruct the ideal functionality to either return the outputs to all parties or to none. This notion of security, though weaker, is also often hard to achieve. An even weaker notion is called security with abort. Here, all parties submit their inputs, and then the adversary receives its output first from the functionality, and then can instruct the functionality to give the honest parties their outputs or not. So we'll be designing our protocols in the hybrid model. In the hybrid model, we'll assume the presence of certain functionalities in the real world with certain levels of security. Examples of such hybrid functionalities include broadcast, OT, or as in this work, we'll use synchronizable exchange. Additionally, the cardinality of a primitive is defined as the number of parties involved in it, either through submitting inputs or receiving outputs. So here are some known results on known feasibility results about MPC. So from the seminal results of BGW and CCD, we know we have information theoretic secure generic MPC for T less than n/3 with guaranteed output delivery. From the work of Fitzy et al., we have information theoretic secure generic MPC for T less than n/2 with fairness. And from the works of GMW and follow-up works, we have computationally secure generic MPC for T less than n with security with abort. So this motivates the following question, that can we hope to get fair MPC for T less than n via some simple hybrid functionality? And by simple here, we mean low cardinality. Recall again, the cardinality means the number of parties involved in the functionality. And the reason we aim for fairness is because fairness is an important property desirable in many practical scenarios like fair coin tossing. And you might recall from Iftak's talk yesterday that fair coin tossing is impossible to achieve in the plane model for T less than n setting, as shown by Cleve. So we will now look at a new primitive, which we call synchronizable exchange, or SYX. Looking ahead, this will serve as the simple hybrid functionality that enables fair MPC for T less than n. So before going into that, let's look at a relative primitive, which we call fair exchange, where fair exchange, so here parties, the primitive is simple. Basically, it allows all parties to fairly learn the inputs of all other parties. A fair exchange can be used to obtain fair coin toss. Parties simply locally pick their random coins and fairly exchange them and then XOR it. What is more interesting is that a fair exchange functionality can be used to construct fair MPC protocols for arbitrary functionalities. The way to do that is the following. So the parties first perform an unfair MPC with security with abort and obtain secret shares of the output of the computation. The parties then perform a fair exchange to obtain all the shares of the output and then reconstruct it. And since this exchange is fair, the output is also obtained fairly. The downside is that this functionality of fair exchange has very high cardinality, a cardinality of n, where n is the number of parties involved. This begs the question of whether there is an inherent need for a complex, that is high cardinality primitive, to obtain fair MPC protocols. Clearly, we don't need it for security with abort, as we mentioned before. And in fact, all we need is the cardinality 2 primitive of OT. Unfortunately, from the seminal result of Fitzy et al., it shows that no primitive of cardinality even as high as n-1 suffices for MPC with guaranteed output delivery. This leads to the confusing situation regarding what is needed for fairness, which is a weaker guarantee than guaranteed output delivery. This brings us to synchronizable exchange, which is a cardinality 2 primitive. It is a reactive primitive that works in 2 phases. The first phase is called the load phase, where each party I submits their input xi along with a tuple capital Fi of 4 functions, fload, ftrigger, phi1, and phi2. And if the tuple of both parties match, then the load phase is successful and both parties receive fload applied to their inputs. And then the functionality proceeds to the second phase. In the second phase, called the trigger phase, either party can submit a witness Wi for the predicate phi I. And if phi I applied to Wi equals 1, then the trigger phase is successful and both parties receive the witness Wi as well as the trigger function applied to I, Wi, x1, and x2. And note that this form of 2-party synchronizable exchange can be easily used to get 2-party fair exchange by just loading the functionality with x1, x2, along with dummy f load 5.1, 5.2 functions that always output 1. And f trigger can simply output the private inputs x1, x2. However, it turns out that it is even stronger. So two-party synchronizable exchange will allow us to go from two-party fair exchange to multi-party fair exchange. For example, 3 parties with pairwise access to synchronizable exchange can perform a 3-party fair exchange. And this result parallels the completeness result of OT of Joe Killian from 88. Just to answer our question, there is no inherent need for a complex high cardinality primitive to obtain fair MPC. And in fact, all we need is a cardinality 2 primitive of synchronizable exchange. So before we proceed to see a sketch of why this primitive suffice, let's recall how the definition of synchronizable exchange looks like. So here is a pictorial description. Okay, so now we'll look at how to construct fair MPC for arbitrary functionalities using synchronizable exchange. So recall that a multi-party fair exchange can be used to obtain fair MPC protocols for arbitrary functionalities. So now we will see how to construct a multi-party fair exchange using two-party synchronizable exchange primitive. So in designing a protocol for multi-party fair exchange, the n parties have some inputs S1 up till Sn and wish to exchange their inputs fairly. And we will assume that parties have pairwise access to the synchronizable exchange channel. For simplicity, we denote the pairwise functionalities by edges shown on the right side of this slide. So in our protocol, what will happen is that each party I will load the input S sub I into each of the n-1 pairwise synchronizable exchange functionalities in which it is involved. Thus, after the load phase of each SYX functionality is complete, we have the following picture. The SYX functionality between each party I and J is meant to fairly exchange the inputs Si and Sj. Then the protocol proceeds in a sequence of n rounds. In any round R less than n, any party can trigger any loaded channel with R values among S1 up till Sn. And that's essentially it. To see why this protocol works, let us consider the case of t equals 4, where party P1 is honest and party P2 through P5 are corrupt. Suppose that in round 3, party P3 triggers the SYX functionality with P1 using the inputs S2, S3, S5. At this point, both P1 and P3 will learn the inputs S1, S2, S3, S5. Then in round 4, which is the next round, P1 can trigger the SYX functionality with P4 using the inputs S1, S2, S3, and S5. And at this point, both P1 and P4 have learned all the 5 inputs, S1, S2, S3, S4, and S5. So hopefully it's clear that the protocol works, assuming the load phases of all pairwise SYX functionalities are complete. The crux of the definition of this synchronizable exchange is that it is possible to ensure that the load phases of all pairwise functionalities are indeed complete before they enter into the trigger phase. And this is the reason for calling this a synchronizable exchange. Essentially, the load phase of SYX will release a certain certificate or signature attesting to completion. And we will require that the witnesses for triggers to include all such certificates before it can be triggered. So load phases of all the n choose 2 channels must be completed before any channel can be triggered. Furthermore, since the trigger witnesses are also released on a successful trigger, if a corrupt party triggers a SYX functionality with an honest party, then the honest party gains the ability to trigger other SYX functionalities and obtain other inputs. Now note that for an adversary to obtain all inputs, it must have a corrupt party trigger SYX functionality with an honest party. And then in the very next round, the honest party will be able to obtain all the inputs. At this point, the honest party can just broadcast this input to all other honest parties so that they can obtain. This completes the sketch of the protocol demonstrating the feasibility result. That cardinality 2 primitive, SYX, is complete for MPC for arbitrary functionalities with fairness. It turns out that this functionality can also be pre-processed. I will not go into the details, but at a very high level, instead of fairly exchanging the actual outputs, So what you do is you fairly exchange secret shares of a key which encrypts the output. I'll suggest you to look into the paper for details. So in conclusion, we have seen that cardinality 2 primitive SYX is complete for MPC for arbitrary functionalities with fairness. One question of interest is whether such a reactive primitive like SYX is an overkill. It turns out that this is not the case. From a recent result of Raghuraman et al. From Asia Crypt this year, we know that no unreactive primitive of cardinality even as high as n-1 suffices for fair coin tossing. Thus, reactive primitives are necessary for fairness. Also note that from our protocol, reactivity was precisely what was enabling the synchronization between different channels. Finally, this work leaves the open question of how one would implement this channel in practice, and turns out that this can be done using bulletin boards and trusted hardware. Details of this can again be found in a recent work by Gadam et al. Thank you.
Any questions? Okay, so let's thank the speaker again.
Thank you.
Thank you. Okay, so the last talk is by Henrik Brocher, the impossibility of surviving deletion of weakly dominated strategies in rational MPC. Please.
So thanks for the nice introduction. I'm Henrik, and the following is joint work with Johannes Blömer and Jan Bobalz on the possibility of surviving iterative deletion of weakly dominated strategies in rational MPC. So fairly long title, and though it features rational MPC at the very end, in our results and in this talk, I will mainly focus on secret reconstruction. Namely, with this toy example, I'd start where we have three parties, we have a safe, and we have a rich guy which puts $60 in the safe. So just $60, not that rich. But anyway, so then he shares the pin for the safe among the three parties. And well, the goal of these parties is now to reconstruct the secret. Well, they want to get the money, right? In order to kind of prevent a trivial approach by kind of brute forcing the secret, we did incur a cost of $20 per long try. And well, afterwards, we provide these three parties a communication network. So we're back to kind of computation and setting. So they share point-wise secure channels, and they have a simultaneous broadcast channel, which just means, well, at the very end of each communication round, all messages which were inserted into this channel are distributed among parties at the same time, so we have no rushing between these parties. Okay, now consider following simple protocol for PI. Just broadcast your share and then reconstruct the secret, right? So this works. At the very end, everyone has every share, everyone can reconstruct the secret, everyone can open the safe and gets the money fairly. Okay, so far so good. However, well, this protocol is not fair to play, since, well, any party could choose to send essentially nothing. Well, party 3 may send nothing at all. The two parties on the right-hand side cannot reconstruct the secret, but party 3 can. So he gets all the money, and well, this is more rational for this party. Also, party 3 could just choose to send a wrong share, and well, this may even lead to the situation where the other parties reconstruct the wrong secret, have to pay $20, and party 3 then reconstructs the secret, gets the $60 out of the safe. Okay, so when I now say it's irrational to play, this is a very intuitive statement. However, we have to formalize this stuff. Okay, and this was done by Halpern and Teague, and then refined by Goldman, Katz, Abraham et al. Roughly 20 years ago in the secret reconstruction game. So again, we have the setting, and at the very beginning of the game, each party chooses a strategy by themselves, and well, it's an ITM, which is just kind of, well, an algorithm which can send messages over the network, and this fixes the protocol then. Afterwards, we have a trusted setup, and okay, the smileys seemingly have changed due to kind of font changes. I hope this will not continue that much. Secret is chosen. Afterward, it is shared, and such a secret sharing scheme, in our case, has property of T and privacy, so just threshold privacy, where T and more shares reveal the secret and less shares don't reveal the secret at all. Okay, and finally, the trusted setup ends with computing signatures on each share, such that kind of we can overcome the second part of the second attack from the toy example before. And then these are distributed among the parties. Now, in order to facilitate mutation, I will just put boxes around a share when it's signed, which kind of visualizes some stuff later on. Okay, now the parties run a protocol, and after the execution, each MI outputs a guess on a secret. Well, this is then called in game theory usually an outcome of some game, where kind of each party's output is kind of put into a tuple of guesses in this case. Lastly, now we can formalize what utility or rationality means, namely each party has a utility function UI, which maps such outcomes to some utility. In the previous example, it would have been, for example, $60 for party 3, when he were the only one to learn the secret, right? And what was then assumed was that in many secret reconstruction protocols and also in MPC, we usually have two properties in such utility functions. Namely, we have the desire to output the correct secret or the correct result of a computation. This was the case in our toy example, right? So we could either pay $20 if we output the wrong secret or get $20 if it's correct. Also, we usually had for exclusivity in such computations. Well, this was the case for party 3 in the toy example as well, where you got $60 instead of $20 when all the other parties got a secret. Okay, now what was considered in the literature is, well, how can we design secret reconstruction protocols which reconstruct the secret at the very end and which are rational to follow, right? In the previous example, we had a protocol which was not rational to follow. And it was indeed not rational to follow in the sense of a Nash equilibrium. So this is the most standard notion from game theory, I'd say. And well, it just means no party can exchange its strategy from the prescribed protocol in order to substantially improve the utility throughout the protocol. Right? In the toy example, it was possible for party 3 to exchange its strategy and thereby increase its utility. Okay, and well, the state of the art back then was, well, such protocols as the simple protocol in the very beginning fail since, well, in the last round of the protocol, a rational party will not send anything meaningful to the parties. Right? And they overcame this problem by randomizing essentially the round in which true shares of the secrets are used. And well, so this then led to the design of Nash equilibrium protocols, which especially holds for this NN private setting. It's especially for this toy example, for example. However, the authors of the papers above also headed for a stronger rationality notion. Since, well, Nash equilibrium they meant, and also we think, is not sufficient in all scenarios. And in particular, they wanted to get the notion of surviving iterate deletion of weakly dominated strategies, or for short, IDOMs. Okay, so what's weak domination? A strategy is weakly dominated if there is another strategy which is never worse against any opponent strategy, but sometimes it's better, right? And intuitively, if we think we have a protocol and we know our strategy is weakly dominated by another strategy, why shouldn't we change to this weakly dominating strategy? Well, and that's the essential meaning behind these lot of works. So behind this IDOTS notion, no protocol prescription or no strategy from our protocol must be weakly dominated. Okay, what we now have shown is that essentially any protocol in the most reasonable settings have at least one protocol prescription or one strategy included, which is weakly dominated. And this was different from what was claimed back then and was then refined later on. So that's basically our results. And the intuition behind this is really, really simple. On the right-hand side, consider the concrete protocol from before, where we have some concrete strategy M3. We can just extend it by a check whether the other parties send us their shares, so their true initial signed shares, together with some leaked message or something. So in the original protocol description, such a message is simply discarded. In our description, it is obviously not discarded, and thereby in the improvement, we get all the money from the sale. Well, and this is not worse than the original protocol if we assume we have a sufficient authentication on the shares, so we can really check whether we got the initial input shares. So in this case, well, the if condition will be false unless there was a forgery, which only happens with negligible probability. Sorry, and thus we get the same utility as M3. And this now generalizes to arbitrary protocols. So we have really black box protocols. So the strategy which we consider as some code, then the first communication round ends, then we have another code. Well, we can improve it by the same check as before. No, in fact, we can't, since this check could also be included in this black box strategy, right? So then we kind of change our check to something where we flip the last bit of the message and check then whether the resulting message ends in some correct signed share. Well, this check could also be included in the black box. And well, what we essentially have proven is that for some case, such a check cannot be included in the protocol, right? So we use the non-uniform setting for this. This can be overcome in a more kind of gray box fashion. However, well, that's kind of the main result for just single party deviations. And yeah, so I think in order to not delay the break too much, I'll already get to my contributions or our contributions, namely we generalize these results in the sense that we also look on what happens if rational parties group together and kind of share their utilities. Well, there we got some results. So the first row of this table just means, okay, this is just a generalization of the example we have seen before. If the shares are signed or authenticated by something which we can locally check, then the previous result applies and the resulting protocols are weakly dominated by something. The second row just applies to kind of more implicit forms of authentication, which are kind of attributed to Reed-Solomon codes. And the last row is kind of, well, if the parties have the possibility to change their shares in order to change the reconstructed secret, but by kind of getting the reconstructed secret can then get the original secret back, then we cannot have a Nash equilibrium at the same time as a not weakly dominated protocol. So that's kind of, these are the main results from our paper. And well, for the future, it's open whether we can show something for coalitions which are non-majority in the last setting. And also, how should we proceed with weak domination, right? So what we have shown is that, well, it's rarely achievable. And back then, it was also shown that there are problems with this notion. However, we think weak domination has some nice features. So look at this protocol. It features a very disturbing if check, which is kind of really bad. But weak domination is really good at pointing out such irrational checks in protocols or something like that. Other notions which also have been put forward in the past don't find such checks. And even though this seems like a toy example, we think some form of rationality notion should kind of rule out such meaningless protocols, we think. And therefore, we are currently looking into new notions which keep the essence of weak domination, but kind of formalize it in a different way. And one such notion was proposed by Hillas and Summit 3 years ago, and it's named iterated deletion of weak flaws. And well, now that really concludes my talk. And yeah, thanks for your attention.
Any questions before the break? Oh,
Um, so I would say that like the examples of weak domination in your case like can be considered contrived in the sense that the parties deviate from the protocol. And do you have any results regarding a weaker, like we could consider a weaker notion that we can consider weak domination, but assuming that the messages adhere to the protocol, the parties might send like invalid inputs like for what they have, but they still have to be syntactically correct, and this removes those example of yours. And do you have any results for that?
So indeed, this is something which we kind of considered as well. It's kind of hard to formalize what you're kind of requiring here, right? So what are kind of syntactically right messages in the protocol, and why should we restrict the rational parties from picking such strategies when choosing their strategies? Since, well, this whole setting, when we consider each agent or each party of this protocol as an individual rational agent, where they have the whole possibility space of all the ITMs, right? Does this answer?
So this could be like sensible in a setting where we would assume that the parties did like the point is that if the message is not syntactically correct, then if the other party would do anything, then the parties need to collude, and like collusion prevention is another kind of worms, but in a collusion-free setting, this could be like reasonable.
Yeah, so I think you already mentioned the thing here. So on the one hand side, it would be possible to kind of include your true share in some meaningful message, so kind of in a subversion way. And well, that's kind of also progress already. So, and therefore we kind of did not took this path by restricting these messages. And also, like I said, I think it's not meaningful for the model to kind of discard some of the strategies already at the very beginning of the game. But we can take this discussion offline. But thanks. So the last question.
great. Let's thank all the speakers from this section again, and yeah, please enjoy the coffee break.